For a year and a half, the sun goes dark. Temperatures plummet and crops fail. Major cities are brought to their knees. A deadly plague wipes out a third of the Roman Empire. Civilizations around the planet are thrown into turmoil. And the course of history changed forever. What could trigger such a global catastrophe? And could it happen again? Around the world and throughout time, weather has played a part in the fortunes of mankind. Violent events in our planet's atmosphere have transformed history. These are the stories of weather that changed the world. This story begins with a mystery. Strange accounts of the year 536 AD, when the sun failed to shine, and the world was plunged into famine and misery. Roman scribes recorded what happened.
The sun became dark, and its darkness lasted for 18 months. Each day it shone for about 4 hours, and still this light was only a feeble shadow. Everyone declared that the sun would never recover its full light again.
And on the other side of the world, it was recorded by Chinese officials.
There was a great famine. As the people fled in search of food, I begged the emperor that the state granaries should be opened to give relief.
1,500 years later, the stories seem more like myth than history. But if they're true, what could have caused such a disaster? What scientific evidence is there about the world's climate in the 6th century? Professor Mike Bailey is a leading expert in the study of tree rings, and they are a good indicator of changes in past climates.
Depending on the balance of temperature and rainfall, the tree decides whether it's going to be a wide or a narrow ring. There's a record built into the tree of climate conditions.
Wide tree rings indicate good years for growth, but it is the narrow rings that are most telling.
We're interested in not just narrow rings, but extremely narrow rings. Rings where the tree has barely managed to put on any summer growth at all.
In his collection, Professor Bailey has a sample of oak found preserved in an Irish peat bog dating from the 6th century.
This is an image seen through the microscope of the same piece of wood, showing the clear rings from 532 up to 535. And then 536, the year of interest. Suddenly in 540, we get this extremely narrow band of spring vessels. And then from then on, no sign of summer growth in the rings for the next 7 or so years.
The narrow rings in this sample confirm an ecological disaster in the 6th century. And evidence from tree rings all around the world tell a similar story. That from 536 AD, the climate suddenly became so cold that trees could barely grow. But what could cause such a huge change in the global climate? Researchers soon began to find clues in the unlikeliest places. By drilling half a mile deep into the ice sheet, the British Antarctic Survey can measure levels of gases that were present in our atmosphere over the last 800,000 years. Analysis of the bubbles of air inside these ice cores has shown that in 536 AD, there was a sharp rise in sulfur dioxide levels in the atmosphere. This date matches the period in which trees failed to grow. What's more, the large amounts of sulfur dioxide in the air suggest the likely source of the disaster. a volcanic eruption. We've seen how volcanoes can cause chaos across the globe. In 1991, Mount Pinatubo in the Philippines erupted. The plume of chemicals in the atmosphere caused a dip in temperature of 0.5 degrees across much of the northern hemisphere. And in 2010, a volcano in Iceland ejected a massive cloud of ash, which blew all over Europe, disrupting international air traffic for 2 weeks. Volcanologist Nick Petford sees and hears firsthand the shock waves of the eruption.
The sounds are really quite incredible. It's something of experience to be this close to the erupting volcano.
Not all volcanoes have the explosive power to eject debris high into the atmosphere. Nick has come to Mount Teide on Tenerife in the Canary Islands to see the distinctive feature of an explosive volcano.
So one of the key ingredients that we need to make an explosive volcanic eruption is gas. And here on Mount Teide, we can see really clear evidence for lots and lots of gas involved in a volcanic eruption. And that evidence is in the form of these shapes, these pits in the rock. I'll show you a piece. These holes in the lava are where gas has escaped from the magma and it's left behind a fossil bubble.
And it's when gas combines with highly viscous lava that monstrous volcanic eruptions can occur. A simple demonstration shows how this works. First, using runny syrup, Nick simulates a non-explosive volcano.
I'm going to force helium gas through the tube from the cylinder, and what we should see is a gas bubble rising up and escaping quite quickly from the top. And what you can see is a huge bubble rising up effortlessly, and it's going to pop at the surface, make a bubble. This is just like a gas bubble rising in magma that's runny. It doesn't make a volcanic eruption explosive because the gas easily travels through the stuff and pops as a bubble at the top of the lava flow.
Next, Nick adds sugar to the syrup to simulate sticky, viscous lava, the sort associated with explosive volcanoes.
So what's happened there is that we've created our own mini explosive volcano. It's more viscous and the gas is having a real problem escaping. The pressure builds up and finally the material is just forced out through the top of the test tube. Just like what happens when you have gas mixed in with sticky, viscous magma.
Back in the 6th century, there were about 20 volcanoes with the right type of lava and big enough to send debris high into the atmosphere. But which volcano was the culprit? Scientists wouldn't rest until they'd found the smoking gun. In the year 536, a dark cloud spread around the world, blotting out the sun. Scientists believe the most likely culprit was a massive volcano. But where was it? They found clues by studying the weather.
When a large explosive volcano erupts, ash, gas, and debris all thrown 10, 20 miles up into the atmosphere. And at that height, they're interacting with the jet stream, basically a fast river of wind moving 200 miles per hour through the atmosphere. And those jet streams flow in both the northern and the southern hemispheres. So generally, when a volcano erupts in the northern hemisphere, it deposits material north of the equator. And if it erupts in the southern hemisphere, it deposits material south of the equator.
But ice core evidence shows that in the 536 eruption, sulfur was deposited in both the Greenland and Antarctic ice sheets, on opposite sides of the world. For this to happen, debris must have been caught in both the northern and southern jet streams. The evidence points to a volcano located near the equator.
For a volcano close to the equator, the first couple of days, a lot of the ash and the debris, it'll stay close to the tropics. But if enough shifting winds come into the picture, some of that debris spread into the northern jet stream, some of it down to the south, well, that same ash and debris can spread across the entire globe.
The most likely volcano to have global reach and the right type of lava in the 6th century, Krakatoa in Indonesia. Its last major eruption was in 1883, when it exploded with the force of 13,000 atomic bombs. 5 cubic miles of debris were ejected into the atmosphere, and the world cooled by more than a degree. But how does the debris from a volcano have such a devastating effect on the world's climate? At the University of Cambridge in England, Dr. Hugh Hunt has done extensive research in this area.
In a volcanic eruption, you've got sulfur dioxide going right up into the stratosphere, which forms tiny droplets of sulfuric acid. We can see the effect of having tiny particles up there with this little experiment involving the water tank. This tank here represents our atmosphere. I have the sun over here, and it's shining through the atmosphere onto the Earth.
When the water is clear, most of the light shines through the tank and reaches the globe. To simulate sulfuric acid particles in the atmosphere, Dr. Hunt adds milk to the water.
Milk is a suspension of particles. There's little particles of fat and protein. This is representing the particles of sulfuric acid in our atmosphere. What's interesting is the effect that these particles have on the sunlight that passes through the atmosphere.
Now a lot of the light is reflected sideways by the particles instead of reaching the Earth. Sulfuric acid in our atmosphere has the same effect. The acid droplets act like tiny mirrors, scattering light away from the surface of the Earth.
If some light is being scattered out into space, then that energy is not reaching the Earth will cool down.
If a volcano blasts enough sulfur dioxide into the stratosphere, it can trigger a dip in global temperatures. And this can lead to disaster. Heat is the engine that drives the world's weather. Without heat, there's less evaporation from the sea, and in turn, less rainfall. The normal pattern of weather goes haywire. Plants begin to wither from lack of water. As crops fail, people begin to starve. Krakatoa's eruption in 536 AD triggered a chain of weather events that left people all around the world in fear for their lives. And the exceptional cold had one more cruel trick to play. The scene was set for a new and horrifying tragedy. In 536 AD, Krakatoa in Indonesia erupted and is widely believed to have spread a dense cloud of volcanic ash around the world, shutting out the sun, causing drought and famine. But the weather had one more cruel trick, one which would help kill millions of people. And it struck at the heart of one of the greatest civilizations the world has ever known, the Roman Empire. In the 6th century, the Eastern Roman Empire was flourishing under a new and powerful emperor, Justinian I. Justinian's seat of power was in Constantinople, modern-day Istanbul, around 6,000 miles from Krakatoa. Historian Dionysius Stathakopoulos has studied this period.
We're in the Church of the Hagia Sophia, the Church of God's Holy Wisdom. It was built by the Emperor Justinian, and this is a sign of his ambition and the confidence and wealth of his empire.
Very few buildings survive from as far back as the 6th century. But here in Istanbul, the Hagia Sophia was completed in 537 AD, just 1 year after the eruption. Yet within 4 years, the city had been decimated by the bubonic plague. plague is usually carried by fleas living on rats and often caused by severe climate change. Drought actually reduces the population of rats and their predators. But when normal weather resumes, the fast-breeding rats recover more quickly than their predators. That's why in 541 AD, as the world recovered from the years of volcanic winter, the rat population rapidly expanded. It was these rats that brought the plague from Egypt to Constantinople.
Constantinople was a very big city. It had a population of around 400,000. It could not feed itself. It needed to import food from the outside. And the staple food, grain, came from Egypt.
Every year, more than 200,000 tons of grain were transported on hundreds of ships from Alexandria in Egypt to the port of Constantinople. And hitching a ride with the grain were the rats. Once on shore, they spread the plague rapidly through the great city. Constantinople was ravaged by the disease.
There were about 800 people dying every day for a period of 4 months. During those 4 months, around 20% of the population, some 80,000 people, died.
Over the next 50 years, the plague spread through Europe and Asia, killing around 25 million people, a third of the empire's population. The once great Eastern Roman Empire was brought to its knees.
It reached ports first, and from there traveled all the way into the mainland, including into some very small rural areas. So obviously its impact was considerable. And at the end of the period, the empire was a much smaller, much more reduced state.
For decades after the eruption of Krakatoa in Indonesia, all around the world, drought and famine continued to bring down civilizations, from Mexico to Mongolia. Global chaos triggered by a volcanic winter, terrifying proof of the power the weather holds over us. And most frightening of all, it could happen again. In the year 536 AD, ash from the volcanic eruption of Krakatoa in Indonesia drew a veil across the sun. Global temperatures plummeted. Civilizations around the world were ravaged by famine and plague. Could such a catastrophe ever happen again? Krakatoa erupted once more in 1883, ultimately killing over 36,000 people and changing world weather patterns for more than 5 years. But this volcano is currently too small to pose an immediate threat. However, there is one place on Earth that is of growing concern to scientists. Yellowstone National Park is one of the most stunning areas of natural beauty in the world, attracting 3 million tourists a year. And it's also one of the most geologically active. 5 miles underground is a huge reservoir of volcanic magma, stretching 30 miles wide and 10 miles deep. This is the world's largest supervolcano, a huge caldera covering 1,500 square miles.
Well, the big super eruption cycle at Yellowstone is once every 250,000 years. There is signs of unrest in the caldera today. There's depressions forming in the ground, the lake is subsiding, then rising up again. So there is strong evidence in places that something's happening beneath Yellowstone.
Scientists forecast the next eruption of Yellowstone would throw 240 cubic miles of ash and dust into the atmosphere, leaving half of the United States uninhabitable. Within 3 weeks, 2 million tons of sulfur would be carried around the Earth by the jet streams.
You would have a dimming or perhaps total darkness because of the ash and dust in the sun for months, perhaps even years in some models. It really is a doomsday scenario.
global average temperatures would drop by up to 50 degrees. And the devastating weather effects could last a decade.
In the 6th century, it's widely held that a third of the population died. I would think that's pretty much the same sort of thing you could expect if one of these big events took place.
With the world's population 30 times larger than in 536 AD, hundreds of millions of people could die.
A big disturbance, like a volcanic eruption, massive climate change occurring immediately afterwards, I think there would be a catastrophe.
Could the weather bring modern civilization to its knees? Only time will tell. But our planet's history teaches us an important lesson, that when a major volcanic eruption next happens, the weather could change the world again.